So let me begin by thanking the organizers for bringing, for conceiving this brilliant conference, and felicitation for TVR. And TVR, very happy birthday for your 85th, and I hope you continue doing the same fantastic physics that you have been doing for 60 years. And I don't know how long I know him. I think I know him from my early PhD days when he visited Cavendish Lab. And we started talking, and all these years I have had opportunity to discuss physics and many other things with him and learn a lot. So just by accident, I discovered that the topic of thermal Hall conductivity is also very dear to TVR, especially in the last 5-6 years. He's been thinking a lot about large thermal Hall response of the underdoped cuprates. So this work has been in multiple collaborations. My current graduate student, Abhijit Maiti, has done most of the heavy lifting, but earlier works by former graduate students Aman Kumar and Jagannath Das will also find mention here. My other collaborators are Subir, who has probably left, and his former student who is now a postdoc in Cornell. How you go? And the work wouldn't have taken the present shape had it not been for extremely valuable discussions with Subhro, Kedar, Yasser, and Darshan. If you want to learn more, you can look up these recent papers, and feel free to bug me also. Okay, so here's the brief plan. So we all might have heard somewhere or the other that the experimental measurement of the chiral central charge, while an extremely interesting quantity to figure out, is both very challenging and no doubt very controversial. So the question we want to pose here is, can the study of the finite temperature thermal Hall response tell us something useful about possibly an underlying chiral quantum spin liquid phase? In general, can we formulate the problem of finite temperature thermal Hall response and learn from this quantity something about the phase that we are in? The second thing is, it's not just hard to experimentally measure and interpret thermal Hall data, but it's also theoretically quite difficult to study thermal Hall response, and in particular, the low temperature limit of the thermal Hall conductivity that gives the chiral central charge. Analytically, as well as numerically, it's a very hard quantity to study. There are approaches. Either you could do transport, which is thermal Hall, or more recently, there are some new wave function based approaches that I will mention. Okay, so we'll do this in using two examples which have very different quantum spin liquid ground states. One is a Kagome system with an abelian chiral spin liquid ground state, and the other one is a familiar Kitaev honeycomb system in the non-abelian chiral spin liquid regime. Okay, so just to flash, I won't touch experiments after the first couple of slides in this talk, but just to give an idea of the kind of difficulties that we are faced with. So here's some very famous data on measurements of thermal Hall conductivity in this Kitaev candidate material, alpha ruthenium trichloride. And what these so this material has magnetic long-range order. It's not a spin liquid at zero temperature. So what these people thought of doing, Matsuda's group, is to subject the system to a magnetic field that suppresses a long-range magnetic order. And what you see is that in the vicinity of the field suppressed magnetic order, the thermal Hall conductivity, the ratio of thermal Hall conductivity and temperature, which measures the chiral central charge, seems to be drifting towards this quantized, half quantized value, which is really the theorist's dream, because this is what you would expect for the supposed Ising topological order that could be realized in this manner. But there were already some doubts about this. And so indeed, some years later, there were other groups trying such things out. And to my understanding, there is no independent confirmation of this half-quantized thermal Hall response. And this is data from Ong's group in pretty much the same parameter regime. So what they have shown here is this ratio of kappa by T as a function of magnetic field. And these individual traces are at different temperatures. And you go down temperature like this. And the dashed line would be where the half-quantized value would be. So you can see that in the same parameter window, which is around these temperatures, you have fallen way below the half-quantized value. And seems that the thermal Hall conductance will just go to 0 as you go to even lower temperatures. And if you happen to be in the vicinity of this plateau, you need to fine-tune your magnetic field and your temperature so that you can hit it. But in general, the peaks go above half quantization. So they kind of are very skeptical about this and instead propose some explanation, more mundane explanation in terms of spin wave bands and non-zero Chern numbers, topological magnons, and so on. This is not the only experiment, and this is the only time I'll show any experiment. So it's just a motivation. Yes, absolutely. Absolutely, absolutely. Yes, yes. So that would eat into what I want to say. So that's it. Yeah. So the bottom line is nobody else has seen this. Now, before I go into my problems, I want to just set the tone for this seminar with some basic notions. And so let's begin with the energy conservation law. And let's assume for simplicity that I'm looking at a gapped phase and it's homogeneous, no disorder, nothing. In this case, I'm then encouraged to expand my energy current in a gradient of temperatures. So this thermal Hall conductivity happens to be the skew symmetric part of the heat conductivity tensor. And as you can see by plugging this expression back into the continuity equation, it does not contribute anything to the energy conservation equation. So now the skew symmetric part, you can easily satisfy yourself that it appears as a boundary contribution to the total heat current through a cross section. And this is in any dimension. So let's look at 2D because this is the context in which my talk is being given. So these are reservoirs. And I've put my sample here in the middle. And there are two edges in the sample which are being maintained at two different, although not so widely different temperature differences. So if you integrate the current density across a cross section of the sample, what you can see clearly is that the heat current due to the thermal Hall conductivity part to this sample is basically a difference of some function evaluated at the two different edge temperatures. So it looks like a boundary effect. So let's consider the edges then. Okay, so we know that if you have gapless edges, which is nice, if that's the case, then there is a modular anomaly in this 1 plus 1D theory that relates the energy current to the chiral central charge. In particular, if you take the ratio of the thermal Hall conductivity to temperature, it gives you a direct readout of the chiral central charge of the 1D theory. So this is what the experimentalists would like to get hold of at low temperatures. Okay, but now the chiral central charge cannot entirely just be viewed as an edge effect, because let's try putting the entire system in a uniform temperature bath. And in this case, you can see there will be no thermal Hall current because everything is in equilibrium. Now, if you deform one or both edges, you cannot suddenly start a thermal Hall response. So therefore, the chiral central charge cannot be really sensitive to the details of the edge, but instead it should be regarded as a bulk property. And the other thing is that you cannot really construct any lattice model that is not a boundary of a larger 2D region that will flow to a low energy theory with a non-zero chiral central charge. All this suggests that we should think of thermal Hall conductance as a bulk property, and you can learn more about that from this paper. So if that's the case, we should be able to obtain C minus, which is chiral central charge, from a purely bulk calculation of the thermal Hall response at sufficiently low temperatures compared to the 2D bulk gap. Okay, then what should be the desirable properties of thermal Hall conductivity? Well, any microscopic bulk formula, as I said, should not depend on the details of the edge, and it should, of course, correspond to what you actually measure experimentally. There's a long history of thermal linear response, which is originally due to Luttinger in 1964. He obtained Kubo formulae for thermal response by introducing these gravitational gravitational potentials, a way of coupling the local Hamiltonian density to some fluctuating temperature background. Okay, but it turns out, and it was found in 1997, that the standard Luttinger-Kubo formulae for thermal Hall and even Nernst responses are not adequate, and they require a modification by energy magnetization in case of thermal Hall and charge magnetization in terms of Nernst. In particular, for thermal Hall, the Kubo contribution needs to be corrected by a part which is proportional to this energy magnetization ME, which is similar to, in spirit, to the charge magnetization in the sense that curl of ME gives you the bound energy current. And the Kubo part is the usual standard one. So you take this Kubo average defined in the usual way. Okay. Now, things looked happy and nice until Kitaev's paper in 2006. Now, it's an enormous paper spanning over 100 pages, and much of which is an appendix. And the appendix contains wealth of information, including his take on thermal Hall conductivity of a lattice system. And there he clarifies in very few pages that the energy magnetization, he doesn't give this name, of course, but the quantity is essentially the same. It cannot be obtained as a unique function of the parameters, such as the temperature. And this, according to him, makes thermal Hall conductivity microscopically, if you try to construct, an ill-defined quantity. And this was further elaborated by Kapustin and Spodinejko in 2020. Now, so what's the resolution? The resolution is provided by both of these. Is that, okay, kappa xy is an ill-defined quantity, but the ratio of kappa xy by t happens to be an exact differential. Yes. Yes. Yeah. So you can define changes in kappa xy by t. These are well defined in terms of parameters of the problem. So in particular, you can easily obtain this differential equation where tau e is what is your proxy now for the energy magnetization. And there is a well-defined microscopic expression for tau e. So it turns out that it is completely antisymmetric in its labels. So if you have a local Hamiltonian and you write down the Hamiltonian as a sum of these local terms, and you define an energy current which is local in terms of commutators of the local Hamiltonians. Don't go and put further favorite terms here because that will mess up everything. And then the tau e has a very clear definition. It can be written in terms of the Kubo averages of the Hamiltonian density and the current energy current operator thus defined. So this is very clear then. You can, on a lattice, at least proceed without any further problems. And by integrating this equation from some reference temperature where you know the ratio kappa xy by T from physical inputs, you can hope to get the thermal Hall conductivity over the rest of the range of temperatures. Okay, so let's put these ideas to work. So we have first example of a Kagome antiferromagnet. So the model consists of Heisenberg antiferromagnet interaction, which I will then perturb with a scalar spin chirality-like term that breaks time reversal symmetry and also parity. And this model without JChi, of course, has a very long history of study, and it was initially the subject of some controversy, whether the ground state is a gapped Z2 spin liquid or a gapless U1 Dirac spin liquid. But more recent works have veered around the latter view, and there is now considerably greater amount of evidence that it's Dirac spin liquid. And more recently, even in 2024, I was surprised to see that even without explicitly breaking time reversal symmetry, the authors of this paper argued that just the purely Heisenberg model has some spontaneous symmetry breaking, and the ground state might even be a chiral spin liquid, which is good for me, at least. Now, but turning on scalar spin chirality, San Kagome, yeah. Now, turning on a scalar spin chirality, interaction definitely stabilizes a chiral spin liquid. In the older works, not the 2024 one, argue that you need to be bigger than some arctan JChi by GH, bigger than 0.05 in order to completely stabilize the chiral spin liquid phase. So then this chiral spin liquid phase is now believed to be in the same topological class as the nu equals to half Laughlin state, which is described by a U1 level 2 Chern-Simons field theory with chiral central charge of 1 and a topological entanglement entropy of half log 2. The calculation of chiral central charge had been a sticking point. It's a very difficult quantity to calculate, but in 2022, there was this very nice work from Kim and his co-workers who proposed that, that instead of studying thermal Hall, what you could do is calculate the thermal current not associated with the local Hamiltonian density, but associated with what we call the entanglement Hamiltonian or the modular Hamiltonian in field theory community. So you do the modular commutator, much like we do the energy density commutator, to get the modular thermal current. And by summing up the modular thermal current across a partition, you can get the modular heat flow, and this directly gives the chiral central charge. So we have actually managed to implement it, and if you do just exact diagonalization and go up to size 30, we can go a little bit more also, then the chiral central charge grows until it approaches 1 for this model. And so it's indeed, the belief is correct. If you calculate the topological entanglement entropy, which you can do by the standard Kitaev-Preskill construction, it converges towards half log 2, which is also expected for this phase. So it's all consistent with a U1 level 2 abelian chiral spin liquid state. Okay, so now that we are on more confident ground, let's just go ahead and construct some field theory, which will allow us to do more controlled calculation of the thermal Hall response. So we partonize the spins, and this is the constraint we have to impose, of course. And now what we do is we use the correct PSG for the Dirac spin liquid. So in the absence of the scalar spin chirality perturbation, let's begin with this ansatz where we make these bilinears on the links, nearest neighbor fermions on the links, and the expectation of this is some complex number. With this ansatz, the original spin Hamiltonian reduces to a tight binding model of hopping fermions on the Kagome lattice with some complex hopping parameters. And the Dirac spin liquid corresponds to the flux of this emergent gauge field to be 0 in the triangles and pi in the hexagons. That's the pattern. Now, if you turn on J-chi, you can self-consistently work out what would be these phases. They change, and now some non-zero flux will appear in the triangles as well. And if you are in a situation where the flux in the triangles is exactly pi by 2, and one in the hexagon is 0, that maximizes, that minimizes your ground state energy. And the gap in the chiral phase is the largest. So this is the regime we'll be working with for convenience, but you can really do all this and work with more realistic parameters. So if you, so for this phases, triangle fluxes being pi by 2, with that we just calculate the band structure. We get 6 bands. Each of the bands is doubly degenerate because of spin degeneracy. And you have a peculiar distribution of the band churn numbers, which is -1, -1, 1, and reversed. Okay. So on top of this mean field, we have to impose the constraint on the parton number at each site, which we do through a usual Lagrange multiplier, which is space and time dependent. So by gauge invariance, this results in vector potentials also appearing on the links of the lattice. So then the idea is to integrate out these bands which are far away from the chemical potential. These are the heavy fermion bands. And then you get some effective theory for the light fermion bands. But since all these bands couple to the gauge fields in the same way, this results in some effective gauge term also to which the light fermions couple to. So I've gone to the continuum limit. I have a theory of Dirac fermions, which are massive. The mass small m is of the order of the light fermion mass, which is J chi, roughly. And this Chern-Simons term is the first term in a gradient expansion. You get because the lower bands have chirality, which don't cancel out. And it's a level -4 Chern-Simons theory. I have suppressed the Maxwell's term, which will also be there. Okay. So now let's go to thermal Hall response. Recall I obtained this expression for the derivatives of the thermal Hall conductivity. If you look at the field theory and you want to calculate it from there on, it turns out that the Kubo and the energy magnetization contributions both depend only on the antisymmetric components of the stress tensor correlators. You can look for more details in Subir's paper in 2020. So the stress tensor correlator is the usual one. You need to calculate correlation functions of this kind. Antisymmetrization means you subtract from this the quantity where mu and rho indices are interchanged. Okay, then the Kubo and energy magnetization components are straightforward to write down. So now the main work would be to calculate these averages. Now there is no small parameter in the problem. So we need to have some control over our calculations and organize our diagrams. So for this purpose, we introduce a large number, NF, copies of the model. And then 1 over NF is the small parameter with which we will organize our diagrams. To leading order, the largest contribution to thermal Hall response comes from free fermions, which are NF in number. And NF equals to 4 in our Dirac's theory, but we have made multiple copies. There is another order N diagram where there is one gauge boson propagator as well. But this we checked is identically equal to 0 because of some unexpected cancellations. So this one doesn't appear in anything. Now, order 1 diagrams might be very familiar to those people who have worked with fluctuation superconductivity. These diagrams have a name like the density of states correction, which is a self-energy-like correction. There's a Markey-Thompson correction, which is like a vertex correction, and the famous Aslamazov-Larkin correction, which involves triangle diagrams. So these triangles shown in dashed lines are actually the sum of 4 processes, and you have to keep all 4 so that gauge invariance is maintained. Otherwise, you start violating word identities, and everything turns out to be incorrect. Okay, so now let's just go ahead and show the results. So this is what you will get for the purely free fermion calculation. You get a chiral central charge of 2, which is wrong, and a high temperature tail, which is a saturation of kappa xy. So you can see kappa xy by T goes like 1 over T. And this is analytically obtained. So this tail is very characteristic, and saturation is also very characteristic of these free fermion theories with no bound on the energy spectrum. Now, if you have a finite bandwidth, the decay will be faster. It will be like, instead of 1 over T, you will get a 1 over T cubed decay. So that also one can easily show. Now, what to do about the incorrect value of the chiral central charge? Well, this is the consequence of doing mean field theory. If you ignore the gauge fluctuations and the contributions they make to the chiral central charge, you arrive at wrong results. So you need to now bring in the effect of the gauge fluctuations. So if you do that, you will have to evaluate the Aslamazov-Larkin diagrams. Now, it turns out that if your temperature is not very high, meaning you are well below the mass of the light fermions, the temperature dependence of these triangles is not there. It goes away. It becomes just a constant. And you end up with much simpler diagrams, which you could have got by just integrating out the fermions, all fermions, right at the beginning. Just have the U1 gauge theory, Chern-Simons theory with level -2, and just write down what the thermal Hall conductivity of this gauge theory would be. So that purely Maxwell-Chern-Simons treatment is rather easy to do comparatively, and you can analytically obtain its contributions as well. So what you get is a renormalization of the chiral central charge. It's a deficit from the free fermion result. And now if you plug in our both contributions together, you get the correct chiral central charge of 1 at low temperatures. But the high temperature results are not correct because this calculation neglects the temperature dependence of the fermion triangles. So this is how the situation has been since 2020. But then we said, okay, let's just look at higher temperatures, because that would also be kind of like being in the quantum critical regime of sorts. And if you do that, then you have to worry about the temperature dependence of the triangle diagrams, which is very tedious, but it can be done. And Avijit, to his credit, managed to pull it off. So what we get is like these two curves. So this is the old curve without the temperature dependence of the triangles taken into account. And this one is our work. So you have at low temperatures the correct chiral central charge obtained. And at high temperatures, what you get is that the Aslamazov-Larkin corrections, they grow logarithmically with temperature. So at some high enough temperature, they will become comparable to the free fermion result, and then your perturbation theory in large N breaks down. So until that point, you have a good window of temperatures to play with, where these log corrections in temperature are your telltale sign of the underlying chiral spin liquid phase. Okay, so I'll end in a few minutes with the second example with the honeycomb Kitaev system. So here, this is the model, and without any time reversal symmetry breaking, there is no thermal Hall response in this system. But now, so we have to add something like a Zeeman term, which we choose to be in the 1-1-1 direction. And let's also add for generality the three-spin chirality term. So once again, we use the modular commutator method to extract the chiral central charge in the low field regime. So what you see here is a finite size scaling data. And as you can see, that as I go to larger system sizes, the chiral central charge computed has this thermodynamic limit value of 0.5, which is expected for the Ising topological order. And the topological entanglement entropy comes to log 2 as expected for this phase. So you can get the same results for the ferromagnetic Kitaev model as well as antiferromagnetic Kitaev model, provided the magnetic field you have applied to is sufficiently small. Which one? This one? Yeah, this is a fit. So this is a fit. Yes. But you can see that the convergence is very rapid. It's actually faster convergence than the topological entanglement entropy, which is more commonly calculated, which converges more slowly like a power law. So you can get pretty much the same results using Parton mean field theory, but you need to put the gauge fields contributions as well as usual, otherwise you'll get garbage. So, okay. So now, if you want to calculate now numerically the thermal Hall response, and you are faced with having to use the Kubo formula with its Kubo and energy magnetization contributions, let me tell you that it's very challenging because both these contributions are typically large and they diverge in the thermodynamic limit. And what you are after is a difference of these two large quantities. Instead, we kind of tried a hack. So what we do is, like, if the system is gapped, this will definitely work. For gapless systems, it should not work. So what we do is we write down the Hamiltonian as a sum of layer terms. We take a strip of the Kitaev system and roll it up so that it's now in the form of a cigar. The energy currents are defined in much the same way. Okay, so now the idea is to put the entire system in a uniform temperature bath. This will give you a zero total thermal Hall current because it's in equilibrium. But nevertheless, that doesn't mean that locally it's zero everywhere. So what happens is that the contributions from the two edges are equal and opposite to each other. And if you now just notice while just doing your local computation of the thermal Hall currents, that there is a sharp decline from the edge to the bulk. If the contributions don't persist deep into the bulk, then you can do some kind of a hack where you sum the thermal Hall currents from one edge to the middle of the sample and forget about the rest of the edge. So you are basically getting a readout of what is the Hall current associated with one edge. Of course, if you go all the way to the other end, it will become zero. And the finite temperature averages are to be performed. We did it using the purification-based finite temperature tensor network approaches. Okay, so here's the result. So if you have a small enough magnetic field so that you are in the Ising topological order regime, the thermal Hall conductivity, in fact, is quantized at half. So we are very proud of this because we can actually get it from microscopic wave functions. And if you then turn on a magnetic field, this peak starts falling very rapidly because you have gotten out of the ITO regime. And also as a function of temperature, as expected, there is a rapid decline in the thermal Hall response. We haven't, so since this paper came first before we did the full field theory calculation, we didn't bother fitting at that time to this temperature dependence to the tail, but I believe that because it's a bounded spectrum, it will be 1 over T cubed, but I'll go and do it. This line. This is very small field. This is 0.025. It's a ferromagnetic Kitaev. Yes, but if you go to, Yes, so I'll tell you. So this dip is because of the finite size effects, because of the finite number of cells in the transverse direction. It's a consequence of doing this 1D tensor network calculation. If we increase the number of hexagons to 4 or 5, then we see this peak broadening and flattening. So, but the position remains at half. However, for that, we have to make even more expensive calculations. So right now, the bond dimensions we normally use is 800, but there we had to go to much higher values, and there were bigger errors in the data. So, this particular low field peak is definitely, I can assure that it's going to shift and also broaden. So unfortunately, we cannot work in a full 2D situation, which would have given, in my opinion, a full flattening all the way down to 0 temperature. So we will always get this decline to 0 at low temperatures because of the discreteness of the energy spectrum and the edge modes. We'll never get a continuous spectrum. With regards to these peaks, they are much less sensitive to the number of cells in the transverse direction, and the position hardly shifts. No, it's not small. It's like, so these, okay, so let me be more clearer. So these peaks are almost insensitive to the field, the number of cells in the transverse direction. These are higher fields, like 0.1, 0.15, 0.5, these three. But this one moves a little bit here, if I increase from 3 to 4. And this one moves very slightly also to the left. So there is some consistent motion, but the effect declines very rapidly as you go to higher fields. We could not, unfortunately, go to even lower fields, because then the bulk gap becomes even smaller, and our calculations require the kind of bond dimensions for which we don't have the resources. So we can't do these calculations. So, however, we are definitely confident that it's all correct, because we can also now independently calculate the chiral central charge directly from the microscopic wave functions, which we earlier didn't know how to do it. So together it kind of complements our understanding. The other check we put on this kind of calculation is that if you go to higher fields, you can do a spin wave analysis and use Kitaev and Kapustin's expressions for the thermal Hall response, because there is a plethora of expressions floating around in the literature, but having burnt one's fingers, that this energy magnetization is the devil in the, whatever. So this, once done carefully, it gives you these series of curves as a function of temperature at different magnetic fields. If you compare, the peak values we get from our numerics are more or less the same as what we get from spin wave calculations at higher fields, but the positions of the peaks are shifted. So the peak values are basically the same as the numerical calculations. So this is another benchmark that, that our calculation is able to interpolate between the Kitaev spin liquid regime, where there is this half quantization, and the high field regime, which is trivial, paramagnet, and described well by spin wave treatment. That's where I would like to end, and thanks a lot.
Any more questions? So, this is just to get your general wisdom. So in the case of the electrical Hall effect, there's an interesting discussion of where the current flows in an actual sample, having to do with the details of screening and how the potential drops. What's the story for the thermal Hall effect? I mean, is there an understanding of, in an experimental sample, where the current would flow?
I don't know if there are experiments to this effect, but when we do this numerical calculation, it's still, if it's a gap system, then it's still concentrated near the edges only.
Well, except you have to somehow think about, given that if you have two heaters, a heat source and a heat sink, when things settle down, what will the temperature gradient look like? Right? So you haven't come across a discussion.
No.
It's potentially interesting. It would certainly been interesting in the case of the electrical.
Absolutely.
Is this energy magnetization a lattice thing, or does it exist in the vacuum? If I take a field theory, for example, Dirac electrons in the vacuum, do they have a current? They have an energy momentum tensor, but is there a curl term in that case?
Yes.
There is.
Yes. In fact, on the lattice, it turns out to be much easier to write it out. But you can go to the continuum limit, and there is a bound energy current which needs to be subtracted out because the energy current that appears in linear response is the transport current. So this.
So in the vacuum, there is an energy magnetization.
Yes.
Thank you.
Let's thank both speakers again.